Bismillahirrahmanirrahim. Assalamu alaikum dear students. I am Arif and I welcome you all to lecture number 32 on the subject of computer organization and assembly language programming. The title of today's session is NASM data types and x86-64 Endianness. Well, in the last few sessions we have done with a hello world of x86-64 assembly program along with the required tool chain, especially the GDB. Dear students, if you have not watched those videos, I strongly recommend that you should watch them first and then fall back to this session. Anyways, the agenda of today's session is shown on the slide. Today we will practically understand the usage of different data types and special tokens in NASM. And in the second part, we will practically understand the Endianness of x86-64 machine. Let us start playing. Let us first talk about the data types. I think we have talked about this when I described the structure of x86-64 assembly program in my previous session. Anyway, just for a recap, NASM provides various defined directives for allocating space for variables, and the defined directives db, dw, dd, dq, dt and do are briefly described in this table, and I have also shown certain examples of declaration for better understanding. For example, this bvar1 is the name of a variable, and this db means defined byte, and this decimal 10 is the initialization value. This CVAR is a byte variable initialized with the single character H, while this message is also a byte variable initialized with 6 characters HELLO and this exclamation marks. Remember, each character is saved as a single byte, so the length of the string named message is 6. And over here this ARR is an array of 3 double words at some contiguous memory location, and these last 3 defined directives actually define floating point variables in single, double and quad precision. Every defined directive also has a corresponding reserve directive that can be used to reserve uninitialized space in memory for variables. And this table over here describes the different reserve directives: RESB reserve byte, RESW reserve word, RESD reserve double word, and so on. And these are some examples for understanding. This BARR is the name given to the memory address where the assembler has reserved 12 bytes of memory. Similarly, this WARR is the name given to the memory address where the assembler has reserved 5 words or 10 bytes of memory. And remember, the memory space allocated is always contiguous in such scenarios. Well, dear students, let me take this opportunity to discuss some special tokens used by NASM that you will come across in many assembly programs. The first is the dollar, which evaluates to the address of the current line. Dollar evaluates to the beginning of the current section. EQU, we have used this. This is used to define constants. And this times, this is a token that is used to repeat data and instructions. And these are some of the examples for your understanding. Remember this message len EQU dollar minus message. This actually calculates the length of this string. This dollar evaluates to the address of the current line, and this message is the address of the start of this string. So their difference comes up to be the length of this string. And this times token actually initializes 64 bytes initialized to 0, to this name 0 buff. Okay, so here is the sample code that I'm going to use to practically understand the concepts discussed so far in today's session. And let us first see what all variables we have created in the data section. Well, this MSG is a byte variable containing a string of characters. Learning is fun with Arif but with a new line character at the end. This len message is the constant declared with EQU directive. This dollar evaluates to the address of the current line, and this MSG is the starting address of this string. So naturally, their difference is the length of this string. Exit status is again a constant with the value of 0. This var1 is an array or sequence of 2 bytes, byte type variables containing 1, 1 and 2, 2. This var2 is a word variable of 2 bytes containing 3, 3, 4, 4. var3 is a double word variable of 4 bytes. And var4 is a quad word variable of 8 bytes. And this repeat buffer, this repeats the byte value AA in hex 128 times. In the uninitialized data section, we have a variable named buffer and have requested the assembler to reserve 64 byte space for this address. And over here we have the code section. Well, these 5 or 6 lines, the initial 5 or 6 lines actually display the message on screen, the favorite message on screen, and these last 3 lines exit the program in a graceful fashion. We have discussed these in detail in the previous session. However, last but not the least, these are the 2 lines which I would like to describe. Move R8, var4. This says that the memory address of variable 4 or var4 should be moved inside this R8 register. Move R9, var4 in bracket. This bracket is actually going to instruct that the memory contents of variable 4 should be moved inside R9. Thanks to Vivek Ramachandran, the designer of SecurityTube Linux Assembly Expert course. I have taken this code from his video. And dear students, let us now move on to the Linux terminal and do a scuba diving inside the assembly program that we have just seen on this slide, so as to have a very clear understanding of what I have said so far. Okay. Well, this is our Linux terminal, and I'm inside the lecture 32. Let me show you the code to you. Sorry for the typos. Data types.NASM. Okay, this is the same code that we have seen on the slide. Let me compile it, NASM rather, assemble it. -felf 64 -g for symbols, and the name is datatypes.nasm. So datatypes.o has been created. Let me link it. Datatypes.o, the name of data types. Okay, so we have the executable. Let me load it in GDB in quiet mode. Data types. Okay, the symbols have been read and we are there. Let me put a breakpoint at start, and we know that start was the symbol from which our program is going to start. Let me run it. We have hit the breakpoint. Let me disassemble. Okay, so this is the disassembly of our program starting from the start function. Once a program is loaded in GDB, we can always use GDB's disassemble command to view the assembly, and by default it is shown in the AT&T format. Let me change to the Intel format. Set disassembly flavor to Intel, and let me do a disassemble again, and well, now it is more readable and understandable. Okay, so let me give a comparison to the assembly which we have written and to the disassembly which this GDB has generated. Let me list the source code that we have written from line number 22 to, let's suppose, 34. I think there should be the, okay, fine. So this was the assembly that we have written, and this is the disassembly. So the disassembly is a bit changed. uh, for example, over here we have used RAX and it has used EAX, assuming that we just want to place a, a single digit inside the register. So instead of using RAX, it has used EAX. So this way the size of the instruction has been reduced. And these are the logical addresses, and this arrow shows that the pointer, the instruction pointer right now contains this address. So this instruction is going to be executed. Moreover, if you want to have a comparison in a different way, you can use the disassemble command with the /m flag. So now you can see this was the code that we wrote, move RAX1, and this is the disassembly of the executable. And similarly, you can go through the entire comparison of the code that we wrote and the corresponding disassembly. Let me clear the screen. Okay, so before I execute the program, let's see the programmer visible registers that are there for us, and these are the registers. Here you can see the 16 general purpose registers, the instruction pointer, RIP, the flags register, as well as the 6 segment registers. We can of course view the remaining registers as well by giving the command info all registers. So now you can see, other than the 16 general purpose registers, the code segment registers, we have these registers ST0, ST1, and so on to ST7 over here. Well, dear students, these ST0 to ST7 are the 80-bit floating point registers organized in a stack fashion, used for floating point instructions. And these registers, F control, F stat, F tag, and so on, they are the control and the status and the tag and other miscellaneous registers that are used with the floating point arithmetic. Maybe at the later part of the course we will be talking about them. This MXCSR, this register contains control and status information for the SSE registers, and following that you have the SSE registers starting from YMM0 to YMM15. So we have these 16 256 bits SSE registers, namely YMM0 to YMM15. Well, probably we have discussed this in some previous session that they are used to pack multiple data items so that the single instruction can simultaneously be applied to all the packed data items. Anyway, we will talk about them inshallah in the later part of the course when we will discuss the floating point instructions and the SSE instructions. Well, dear students, we can always print the contents of any one of these registers using the print command. Let me show you how we can do that. Print/x. Let me show you the contents of the instruction pointer. So you can check out that the contents of the instruction pointer are 40100, which are the same as shown over here, because this is the instruction pointer and this is the next instruction to be executed. And similarly we can display the contents of other registers. Let me show you the contents of E flags, $E flags in binary. Okay, so E flags, so it is flags. So these are some of the flags which are set. And of course you can print the values of any of the registers. Let me print the value of R11 in hex format. Okay, it contains 0. And of course, dear students, we can modify the contents of these registers as well using the set command. Let me do that as well. Let me say set, sorry for the typos, dollar R11 is equal to, let's suppose 0xAA. And now let me check out the contents of R11. So it is changed, and we can print that in binary as well, and we can of course print that in any other format, octal as well. So that is great. Let me clear screen. I think that's enough of information about the registers. So let's fall back to our assembly program. Let me list that line number 7 to line number 25. Okay, so here are the variables in which we are interested in this program. I can always do info variables. So you see these are the variables, name of the variables with their corresponding addresses as well. Now let us view the contents of these variables or memory addresses using the GDB's examine command. Let me clear screen. And before I use the examine command, let me first view the help page of examine command using the help x command. So this is it. Well, dear students, the examine command is followed by a slash and fmt, and then we have an address. So this is the address, memory address which we want to examine. And this fmt is a repeat count followed by a format character and a size letter. Well, the repeat count by default is 1, and the format character can be O for octal, X for hex, D for decimal, T for binary, and so on. And the size character can be B for byte, H for half word, W for word, and G for giant. Okay, so that's fine. Let me say info variables again. Okay, so let's first see the contents of the 32-byte message variable, MSG. I want to see the contents of this variable. So x slash 32 in character, and I need to give the address, that is message. So here you see. So this message contains LEAR. These are the bytes that are there inside this string. And at the very end, you can see the new line character as well. Let's see the contents of var1. I just need to replace var1 over here. And of course, we know that, let me move on to the slides. var1, okay. var1 is an array of 2 bytes. So let me say I want to have a count of 2 in hex and bytes, and here you go. So var1 contains 1 1 and 2 2. var1 contains 1 1 and 2 2. So that is great. That is great. Let's see the contents of var2 as well. And if I go back to the slides, we can see var2 is a word, 16-bit words containing 3 3 and 4 4. So let me say that I want to read a half word, H. So this is var2, and if I want to read var3, that is a 32-bit word, so I write W over here, and AABBCCDD, these are the contents of variable 3. AABBCCDD, that's great. So let me show you the contents of variable 4 as well, and since that is a 64-bit variable, so let me write G over here, and there you go. So these are the contents of variable 4, and this is the address. Okay. Now let us see the repeat buffer. This repeat buffer containing 128 bytes, each containing AA in hex. So let me fall back and we want to, let me clear the screen. I want to examine the 128 bytes in hex of this address. Repeat underscore, and let me correct this as well. This is ampersand, and there you go. So these are all the A's which are there inside the memory location pointed to by repeat buffer, and this is what we have written over here using the times token of NASM. That is great. Okay, so finally let's talk about the uninitialized variable as well in the .bss section. The uninitialized variable is buffer, and we have reserved 64 bytes for that. Let me examine that memory location as well. 64 bytes display in hex, and the name is buffer. Okay, so you can note that the uninitialized global variable buffer is initialized with these zeros. This is the default behavior of most assemblers and compilers. Okay, so we are done with the variables. Let us again see the disassembly of the program. Okay, well, once again note the program counter at this address. Just note the first 5 digits, 401000. Confirm it, /x $rip. Okay, so let us put a breakpoint at this address. Let's suppose at this address now. Okay, make a breakpoint at this address. Let me copy this. Let me say break, put an asterisk, and paste that address over here. So we have placed a breakpoint at this address, and let me continue the execution of the program up till this address, and you can see that this portion of the code up till here has printed this favorite message, learning is fun with Arif Bhatt. And now the control is at this instruction, move R8, VAR4. Let me fall back to slides. We are over here, move R8, VAR4. Remember, over here the address of variable 4 will be moved to the R8 register, and in this instruction the contents of this variable will be moved to R9 register. Let me do next and another next, and now let me check out the contents of R8 and R9. Let me print /x $R8. Okay, sorry. So it contains this address 402028, which should be the address of the variable var4. Let me check that out. Var4 402028, 402028, and of course R9 will contain the contents of var4, and the contents of var4 are A, B, B, C, C, D, D, and so on to 44. Let's do that as well. R9. There you go. Note the contents of var4 in R9 register. Let us now run the program to completion by pressing C and enter, and there you go. The program has exited normally. Let me quit GDB. Okay, so dear students, I strongly recommend that you all must make your hands dirty by doing all this on your machine with your own hands. Just don't watch the movie, watch this video, do it practically, and you can get the codes from the Bitbucket repository. Meanwhile, let me fall back to slides. Okay, so now is the time to practically understand the next concept, and that is the concept of Endianness of a machine. And I think we have talked about this theoretically in some previous session, but let me quickly brush up. Well, dear students, in computing, endianness is the order in which multi-byte data is stored or retrieved from computer memory. And endianness is primarily expressed as big endian or little endian. Big endian system stores the most significant byte of a word at the smallest memory address. That is the most significant byte first, and this is used in the MIPS and the Motorola, as well as all the data on the internet is also in big endian. On the contrary, little endian system stores the least significant byte of a word at the smallest address. That is least significant byte first. And little endian systems are x86 and ARM. And this is the example. If you want to store a 8-byte number in memory, and suppose the number in hex is 11223344 so on to 88, and let's suppose that these are the addresses of memory 01234567. In case of little endian, the least significant byte, that is this 88, will be stored at the address 0, and this 77 at address 1, 66 at address 2, and so on. And in case of big endian, the most significant byte, that is this 1 1, will be stored at the lowest address, and then we have 2 2 and so on. So I hope this makes sense to you all, and this is a sample code using which we will verify and understand the endianness of our x86 64 machine. And note these two variables. var1 contains 8 bytes starting from 1 1 2 2 3 3 so on to 88, and this var2 contains the exact reverse of it. Okay, so let's move on to the slides. Okay, let me clear the screen, and now let me show you the program first. Endian.NASM. So this is the program which we have seen on the slides as well. Over here, this is the data section containing two variables, and this last 3 lines of code are just for exiting the program, and these are the 2 lines of our interest. We are actually reading the contents of variable 1 and placing them in RAX, and then we are reading the contents of variable 2 and placing them in RPX. Okay, so this is quite simple. Let me assemble NASM-F ELF64, the file format, -G for debugging symbols, Endian.NASM. Let me link using LD, the Endian.O file, and let me name it Endian. And now let us load it in our favorite debugger, GDB, in quiet mode. Okay, the program is up and running. Let me set the disassembly flavor to Intel, which is more convenient to read for us, and let me put a break at the label start, and let me run the program, and let me disassemble. Okay, so this is the code. You see, this is the first move instruction, which is moving the contents of var1 in RAX, and this is the second move instruction, which is moving the contents of var2 in RPX, and these 3 lines are actually for a graceful exit. Let me show you the variables, info variables. So these are the 2 variables which we are interested in right now, var1 and var2. Remember, on the slides over here, var1 contains 1 1 2 2 3 3 4 4 and so on. Let's examine the memory. Examine 8 bytes of var1. Okay, so 1 1 2 2 3 3 4 4 seems okay. Let me examine the contents of the address var2, which is the exactly reverse of it. And now the program counter is at this address. Let me execute these two instructions now by pressing next and next again. Okay, so let's check what is there in RAX now by print slash x dollar $RAX. Okay, so my dear students, note this var1 contains 11223344, and this 11, which is there inside the memory at the lowest address, is stored as a least significant byte, and this 88, which is stored inside the memory at the maximum address, is stored on the most significant byte side. Hence, this proves that the machine on which this assembly program is running is Little Endian. Let me print the other registers as well, RBX. And over here you note that this variable 2, the byte at the lowest address in variable 2 is 88, and this 88 is there at the least significant byte position, and the byte at the maximum address for var2 is 11, and this 11 is there at the most significant byte position. So this verifies again that our x86-64 machine is a Little Endian machine. Let me continue this program, exit it normally, let me quit the GDB, and let's fall back to the slides. Okay, so that is all for today's session. I hope it was informative for you all. If you have liked it, please subscribe my YouTube channel and share it with your friends. Wish you all the best, happy learning, and Allah Hafiz.